So yeah, you come up with these rules, these axioms that if you use these axioms, then you know paradoxes like that don't happen. If you find another paradox, then okay, how do we prevent that from happening? Let's go ahead and add another axiom, right? So you add axiom, 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 and then you say that, all right, this is the minimum number of axioms that you need to be able to prove this thing that is well established, or that we have a well established idea. This set of axioms over here and this set of axioms over here, they're equivalent to each other, right? And in fact, that's what we're going to get into today, at least with computation, this is the last module, of course, for this course. You know, what can be computed? Can anything be computed? So I'll open it up with this one question: can computers solve anything? Right now, you're all computer science majors, or minors, or whatever. You've taken this course, so confirmation bias here. You have a probably more than likely a positive view of technology, right? But what kind of question is that? That's a question of philosophy, right? We can't really answer that because it's kind of opinion based. You can come up with a long list of ways that technology has made our lives worse. You could come up with a long list of ways that technology and computers have made our lives better, right? And then you can argue back and forth on whether or not the first outweighs the second. So can computers solve everything? Can they solve anything? Right? Well, let's go ahead and rephrase that question. So consider the following statement. Algorithms solve problems, right? So it's kind of a reformulation of the question. In other words, can any algorithm solve any problem? Or for any problem, does there exist an algorithm for it? And now, what do you think the answer to that is? No. Okay, so no. There might be some problems that are not solvable by an algorithm. And that's what we'll actually build an answer to. There's still a problem here. This is no longer a philosophical question, but unfortunately it falls short in the definitions. What is an algorithm? Have you ever come up with an actual mathematical definition of what an algorithm is? We were talking about set theory, right? You can say that a set is a collection of unique similar elements, right? That's pulling the definition out of the dictionary, though, right? That's not a mathematical definition. For a mathematical definition, you need to come up with these 9 or 8 or however many there are axioms that formulate the basis of Zermelo-Fraenkel set theory. Now that is a mathematical definition, right? 300 pages of Principia Mathematica to show that 1 is equal to 1, or something. 1 plus 1 is equal to 2. So if you're going to ask this as a mathematical question, you have to come up with a mathematical language to even begin to ask the question. An algorithm is nothing. What is an algorithm? It's a series of steps for solving a problem, right? Well, then it becomes a tautology. Right? If you pull something out of the dictionary that says an algorithm solves a problem, right? Then of course it's going to be the answer is yes. But that falls short because that's not what we mean by algorithms. What does it mean to solve a problem? We've already seen many different variations on problems and algorithms. It spits out a yes or no answer, decision versions. It spits out an actual path. Does there exist a path from S to T? If so, then it spits out a sequence of vertices that get you there. What's the best path, right? Optimization problems, functional problems, decision version problems, counting problems. How many paths are there, right? So to solve a problem, that's not entirely precise. Right? And what is a problem? We have we have a dictionary idea, a dictionary definition of idea of what that means. But what we need to do is we need to take these 3 elements: algorithms, what it means to solve, and what it means to be a problem. And what we need to do is we need to establish mathematical definitions for each one of these 3. Okay? That's just the groundwork. That's laying the groundwork for answering the question: can computers solve everything? Can algorithms solve any problems? Does there exist an algorithm for every problem out there? Okay? To even be able to begin to answer that question, we need to start establishing the tools by which we can ask the question, right? Again, these statements are plain old English. They're dictionary words with dictionary definitions. They fall completely short with respect to the math involved. So what I'm going to do over the next week or so, probably just the 2 or 3 lectures, is translate that statement, algorithms solve problems, into Turing machines decide languages, or decide languages. So what is it? You've probably heard of Turing machines before, that, or maybe not. That is the accepted definition of what we mean by an algorithm. Alternatively, you could come up with, and people have, like lambda calculus, and show that that model of computation is equivalent to the other model of computation. But we need to define what a Turing machine is first. What does it mean to decide a language? And by the way, what does it mean to be a language, first of all? Right? So that's where we'll start. What is a language? Languages. Languages are kind of like, human languages, English, Chinese, Japanese, Spanish, whatever, in that they have specific components, right? So let sigma be 0, 1, the set containing 0 and 1. This is our alphabet. Now, that's just me getting started here, all right? You could expand this definition of an alphabet to be any number of symbols. For example, in English, our alphabet is A through Z, right? For Japanese, it would be 46 hiragana, 46 katakana, 48, what is it? 48, or 46, 48. Plus all the diacritics, plus tens of thousands of uncommon and only a few thousand or a few hundred common kanji characters, right? So that would be the alphabet for a different language. For Spanish, it would be A through Z, but also the diacritics, the tildes above the N's, the ñes, or what are they called, right? All that stuff. For us, it's going to be binary, 0, 1. Why is that enough? Take English, for example, A through Z. Do you need 26 symbols? No, what can you do? You can encode those 26 symbols as ASCII text, and now you are talking about an alphabet over 0, 1. So for our purposes, it is simply going to be sigma is binary. It's a binary basis, right? A string or word over sigma is a finite sequence of symbols from sigma. Right? So for example, you have, say, 0, right? The symbol itself is a word, right? It's just a word or a string of length 1. You can formulate any binary strings that you want, right? Oh, sorry, there we go. Or you can also start with zeros. Leading zeros are allowed, right? You don't truncate those because it's not necessarily representing an integer. It is representing a string over this alphabet, right? Or say if it's all zeros, right? 0, 0, 0 and 0, 0, 0, 0, right? You could have 3 zeros versus 4 zeros. Those are distinct words. And then there's this very special word, or word, called lambda. Sometimes it's they use epsilon instead, is the empty string. Okay. Let me close that off. There we go. Lambda is the empty string. And what you need this because basically this is what's called a monoid. A language is a monoid under concatenation. If I have this string and this string, concatenation means putting those two together, and then you have a string in the same in the same domain. Well, what does it mean to have an identity element, right? If it were not concatenation, if it were multiplication, x times what gives you x back? X times 1. So you need the same identity element under this kind of monoid. So what this string right here concatenated with this leads to the same string. Well, what has to be that string? The empty string. Right? And it's commutative, but you don't necessarily need that. Okay. All right. So there we go. So a set the set of all finite strings over sigma is denoted as sigma star. There we go. Just making sure that that's rendering correctly up there. So, for example, sigma star, let me just go ahead and cut and paste this so I don't have to write the LaTeX code over and over again. Let's start with the empty string, right, the lambda. Then we'll start with all strings that are of length 1, 0, 1. Then we'll go with all strings that are of length 2, 0, 0, 0, 1, 1, 0, 1, 1. Right? You can count, for each particular length, you can count in binary, making sure that you're not missing those leading zeros. Right? Dot, 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 dot. That's off to infinity. Right? So why do we use the star? By the way, that's called the clean star, K-L-E-E-N-E. Right? Where has anybody seen that kind of notation before? No? Let me come over here. You've never seen anything like this, like a dot star? No? Or say A through Z star. It's kind of like the power set in that take everything in this set and take all possible concatenations with everything else. Unix. So 251. These are, yes, it's kind of like a wild card. Regular expressions. The dot here, that matches any single character. The star here means 0 or more occurrences of it. So in other words, if you think about this as sigma, any single character, and then star, the clean star here, that means it's going to match anything. Right? You could have regular expressions like, say, 0 through 9. There's one set, 0 through 9. That's the second set, 0 through 9. And what that's going to do is that's going to match any sequence of 3 digits. Right? Because you have 1, 2, 3. You could have, say, a phone number that begins with an area code of 4. So you could have 4 and then 0 through 9 and 0 through 9. So it begins with a 4 and then is followed by exactly 2 numbers, 2 digits. Okay. What if you put a clean star on this? Well, now that's going to match any sequence of digits, including the empty string. Right? So that's where this comes from. If you have now had an occasion to learn regular expressions, definitely do so because they are super, super powerful in programming languages. And where do we get that star? Well, just like anything else, it came from mathematics, so we put it into our computer science stuff. Right? All right, so that's the set of all possible finite strings. Now we can define a language. A language is a subset L, and so I'm going to use the letter L here to denote a language. Subset equal sigma star. Right? So it's just some subset of finite strings. Okay. A language may be finite, be a finite set, or an infinite set. But all the strings it contains are finite strings. You can talk about infinite strings if you really want to, strings that go off into infinity. You know some of them. Pi is an infinite string because it never repeats, it never terminates. Right? It's an irrational number. But it's over 0 through 9. Of course, if you encode it in binary, now it's over 0 through 1, right? Okay, so here's my claim. Languages are equivalent to problems. Right? Why? Give me a problem that you've solved this semester. Closest 2 points. So closest 2 points in the Euclidean plane. What was the input on that? It was a list of numbers, x and y, right? And what was the output? It was just two numbers, right? Now, when I gave you that text file containing those x and y coordinates, the first one being the number of points in the input file, you looked at it as a regular old text file, right? And you saw 3.542, comma, or maybe there was a space, I don't know, 10.789. Is that how it was represented in a computer, though? In a computer, what is it at the end of the day? That are encoded in binary, right? So your input was just a bunch of binary, right? Now, how does that jive with the problem, right? So what's the output? Also a binary string, right? So I can kind of see the justification there so far of everything is binary at the end of the day, at least as far as a computer is concerned. Take whatever type of input you want, encode it in binary, and you've got yourself a finite string made up of zeros and ones, right? That's the input. Yeah, go ahead.
You mean that, but the solution I output might not be able to be taken back in as an input.
So hold the thought on what the output is for a second. Let's go ahead and limit our scope first, okay? So the scope here will be to decision problems. Remember that a decision problem is a yes or no problem, right? That a decision problem, so give me another problem that was definitely a decision problem. Say graphs.
Does this have a, what's it called?
Hamiltonian cycle? All right, so here's a graph. Encoded in binary, right? Just a bunch of zeros and ones. And you need to give me a yes or no answer. Does there exist a cycle or not, right? Does there exist a Hamiltonian cycle or not? Does there exist a Hamiltonian path or not, right? Yes or no. So that's what a decision version is. The output is simply a yes or a no. How could you encode a yes or a no? Yes, no, right? So even the output here is a finite string. Given an integer x, is it prime or not? That's a yes or no question, right? So it is simple enough to encode problems as binary, right? Problems, that is inputs, can always be encoded in binary, right? So for example, here's a problem. Example. Let me go ahead and define a set. Right? And for this, I'm just going to go ahead and grab this. Right. Here's a set using set builder notation. I want to consider all graphs G such that G is an acyclic graph. Go ahead and change that plain old English definition there with whatever your problem is. That it's a Hamiltonian graph. That it's a what else did we say? Prime or not, whatever, right? It's just a set. It's a set of all graphs that are acyclic, right? You can also consider the complement of that set, right? So let's go ahead and think about that for a second here. A graph G would be a member of this set if it did not have a cycle, right? And not contrapositively, but complementary here. A graph G would not be a member of this set if it did contain a cycle. So here's a graph G. I want to ask the question of whether or not it has a cycle. How could I rephrase that question? Given G, does it contain a cycle or not? Can be transformed into what? Is G in, and I didn't give this a name here, but I'll go ahead and call it L just for short, in L, or is G not in L? There we go. So I'm simply asking, I've rephrased this conceptual question of whether or not it has a cycle, and I'm asking whether or not it's in the set. If it's in the set, then it's acyclic. If it's not in the set, then it contains a cycle. Right? This is all just definitions for so far, right? Now what we're going to do is we can then encode, we can then change the question problem into a language question problem as follows. We will encode a graph G into binary. And what we usually do is use Langle-Wrangle here. Langle, Wrangle, there we go. That will be the encoding, right? This is a binary encoding of a graph G, right? How would that work? Do we care? Right. How would that work just really, really quickly here? How, if I've got, like, say, A, B, C, and D, right? And there's my graph. How would you go about encoding this thing? Well, you have 4 vertices, right? So I'll encode A as 0, 0, B as 0, 1, C and D 1, 0, 1, 1. That looks familiar. If you were to treat these as binary numbers, what is this? 0, 1, 2, 3. That looks really familiar from all of your assignments, right? All right. How would I actually encode the graph then? 0, 0 is connected to 0, 1. These are my edges. Right. What else is connected? 0, 0 is connected to 1, 0. 0, 1 is connected to 1, 0. And finally, 0, 1 is connected to D, which is 1, 1. Right? So, altogether, you could say, encode N. Here's the encoding of G. Right? You don't have to encode every single vertex. You could just encode the number of vertices. Right? It would end up being an encoding of N, the number of vertices, in this case 4. Then maybe a semicolon. And then a comma delimited list of, actually you don't even need comma delimited list, but I'll go ahead and put in a comma there anyway. 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1. All right, I think I screwed up, but that's all right. All right. So, does that look binary to you yet? Is that purely binary? Nope. So let's go ahead and encode N here. 4 is what in binary? 1, 0, 0, then a semicolon, and then all the rest of this stuff up here. Copy, paste, there we go. That looks like a little bit more binary to me, but is it purely binary yet? Nope, what do I have? Commas, I've got semicolons, and I've got colons. All right. Go ahead and encode those as binary. Right? So, could I do 0, I've got 3 here, so I need at least 2 bits. 0, 0, 0, 1, 1, 0. And then replace all those in this one? I couldn't do that. Why? I already have zeros and ones and 1, 0 and 0, 0, 1, 1, all that stuff. Have we looked at something this semester that would be able to solve that problem, though? What? Huffman coding. Huffman coding produces what? A prefix-free code. So that you only need pure binary strings, but you have an unambiguous way of expressing them. ASCII is good enough too, right? So if you wanted to just reverse all this that I was just talking about, forget it, it's just ASCII, forget it, it's just a bunch of Python code that ultimately is a bunch of binary, right? You're all computer scientists, you know binary. Everything's binary. Right? So this is going to be my placeholder here for encoding a high-level idea, like a graph, or a high-level idea like an integer, or a high-level idea like an input to a 0-1 knapsack problem, right? All right, how does this become a question about languages, right? Define a language as follows. I'm just going to simply take this definition that I gave up here, that L is the set of all graphs that are acyclic, and I'm going to go ahead and redefine that language, there we go, as all encodings, wrangle, such that G is an encoding of an acyclic graph. And there is my question about languages. Now, what are the elements of L? L consists of finite strings, right? Each finite string, X in L, represents an acyclic graph, G. The finite strings that are not in L are either encodings of graphs, G, that are not, that contain a cycle, or encodings that are invalid under whatever encoding scheme you came up with. So you're all computer scientists. You know that you could write a faulty program that is not compilable, right? You could write if you just mash the keyboard with a bunch of zeros and ones. Is that guaranteed to be a valid binary file that can be run on the computer? No, right? So there are valid inputs, and there are invalid inputs. We don't consider those invalid inputs. They're not in the language, and technically they're not in the complement language. The complement language here would be the set of all binary encodings of graphs that contain a cycle. Okay, it's just a small technical detail there. All right, so what other type of problems can be encoded in a language? Other types of problems, right? This is a technical detail. In other words, I just want to hopefully we understand at this point that my claim has been satisfied. Languages are equivalent to problems, decision problems. But now I'm also going to go the extra step here and show you that they are equivalent to, say, optimization problems. So what about optimization problems? Right. For example, what's one optimization problem that you've had before? Okay, so I don't want to do that one. Well, let's do Hamiltonian path. All right. So consider the following: given a graph G, and I don't know. Given a graph G, you want to determine the length. Oh, actually, no. Here, let's go with shortest path. All right. Given a graph G and two vertices, say X and Y, what is the length of the shortest path between them? Right. That's an optimization problem. Right. That's pretty straightforward. That you want to minimize K, or you want to minimize the path between them. So here's an encoding. Right. So in addition to the wrangle, there we go. In addition to the graph G and of course X and Y, I will go ahead and encode all of those because those are all part of the inputs. What I'm going to do is I'm going to augment the input with another variable here, K, right? Comma K. There we go. There's my encoding, and this will be this encoding will be in the language if there exists a path from X to Y in G of length K. Now, how do I do my optimization problem? Here's a graph G. What is the length of the longest possible path between any two vertices in a graph with n vertices? N minus 1, right? Because if you've got n, if you have a path of length n, what happens? that's a Hamiltonian cycle right there, but it's a cycle, right? So you want the shortest path. Well, what's the shortest possible path between x and y? One edge, right? So it's anywhere between 1 and n minus 1, right? So start asking questions over and over and over again. Well, is the shortest path n minus 1? So let's say that n is 5. So is the shortest path of length 4? In other words, I put in 4 for k for my input, and I ask the question, is that in the set or not? Is there a shortest path of length 3? Is there a shortest path of length 2? If this is yes, 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 and then finally yes, right, well then you know what the shortest path is. It's 1. If it's yes, yes, no, right, then what's the shortest path? The last question that you asked was a yes, so 3. Right? So in other words, you can encode optimization problems as decision version problems. All you have to do is parameterize it and say, well, we'll go ahead and encode k as part of the input as well, as part of the problem. Right? What about accounting problems? Counting problems. Given the graph G and 2 vertices, how many distinct paths are there from x to y? And again, what would you, how would you encode this? Same encoding as before, actually. This encoding will be in the language if there are k paths between x and y, right? And then, of course, you can come up with bounds on that. The total number of possible paths, distinct paths between them is going to be something like 2 to the n, right? And then, of course, there could be 0 paths between them. So anywhere between 0 and 2 to the n, you ask those questions over and over and over again, right? In fact, what's the optimal way of asking those questions? What I just did, the last example I gave you was, does there exist a path of length 5? No. Yes. Does there exist a path of length 4? Yes. Does there exist a path of length 3? ... Right? I did it in a linear fashion. Is there a better way? Like what? Split it in half. That's called not linear search. 5, 4, 3, 2, 1. Right? But instead, split it in half. Does there exist a path of length 3? Yes. Oh, okay. Then, if you want a shortest path, you go that way. If you want the longest path, you go that way. Divide and conquer binary search on the length of k. Right? And that gets you the optimal way of asking those questions. Right? You also have functional versions, right? So, functional problems. Given graph G, X, and Y, we know what the shortest path is. We know we know that there is a path, right? We want to output the shortest path X to Y. In other words, a sequence of vertices. Right? Okay. So here's the encoding. What I do is, instead of encoding a number, k, I go x, y, and z, right? And now the question is G a graph such that the shortest path from x to y contains z as an intermediate vertex? You've seen that before, right? In fact, that's how Dijkstra's algorithm solved the problem. The output, it gave you the successor. Which one do you go to next? Or Floyd-Varshall's gave you the predecessor. If you want to go from x to y, how do you get there? Well, first of all, you have to go from x to z, right? And so the question becomes, is that z, right? And if so, okay, great. Yes, I will continue and move on. If the answer is no, that's not z, try a different z, right? Until you get the answer is yes. And then you can build that path. But this is just a yes or no question, right? It outputs yes or no. But from that yes or no question, you can actually build the solution. Right? Okay, so hopefully I have justified enough that languages and problems are the same thing. You only need to deal with sets of strings over a binary representation, right? Now let's talk about computational models. This is going to be the other thing that Turing machines decide languages. What does it mean to be a Turing machine? But before we get to there, we need to talk about lesser computational models. Right? So to start, we'll look at finite state automatons. We're not going to get into it because this would actually be, say, 8 weeks in 428. 428 is going to be computation, finite state machines, et cetera, and you start out with finite state automaton. In fact, I'm not even going to write it out. I'm just going to go ahead and cut and paste my notes so that I don't have to write it out. An FSA, or finite state automaton, is a 5-tuple. All right, so this is the technical definition. Don't get hung up on it because we're not going to get into it too deeply. But do understand that there's a finite set of states. Right? In a computer, there are a finite set of states. It's just that there are a lot of them. Right? You can think of this as like a coin, a finite state machine as a very simple coin-operated machine. You put in a quarter. Well, now it goes to a different state. There's 25 cents in the machine so far. You want to buy a pop or something. Right? You put in a dime, and it goes from the state representing 25 to a state 35. Right? You decide, oh, okay, I don't have enough money to buy this. So reject. It spits out your quarter and your dime, hopefully, right? And then it goes back to the 0 state. It doesn't have to always go like that. If you went with a dime and then a quarter, you would go from the 0 state to the 10 state, representing 10 cents. Then you would go to the 35 state, representing that you put in a quarter second, right? And it's all just these state transitions from one state to the next. Sigma is our alphabet, zeros and ones, instead of 10, 20, 30, whatever. It's just a bunch of zeros and ones. And then delta here is what's called a transition function. Given the current state, given 1 bit of the input, where do you go to in your state next? Given your current state, given that you put in a dime, you go to that current state plus 10, that's just another state. Q naught is your initial state because you've always got to start somewhere. And then there is a set of accepting states, and by exclusion, the rest of them are what are called rejecting states. So now to understand this, it's going to be much easier to understand this if we just look at an example. 10, computation, here's our first automaton. Okay. Now, let's go ahead and look at what happens on several inputs and how this computation works. So here's my input. Say it's 0, 0, 1, 0, 1, 0. Okay. How many bits are in the input? 1, 2, 3, 4, 5, 6. Each bit results in one transition state. You don't go back and forth. You can't remember where you've been before. You only have local information. This is why it's a very, very simple, but somewhat powerful, but still not as powerful as, say, a Python program, sort of a computational model. Okay? So I'm going to go ahead and highlight this here. We come in on this initial state, so we're right here. Now we read 0. So if we're on this initial state, where do we go once we've read a 0? That's what these transitions are for. If we read a 0, we go over here. If we read a 1, we stay in the same state. Right? So now let me go ahead and track where we're going here. We come into this state right here. We read a 0. And where do we go next? To this state right here. Okay. We read another 0. So where do we go? Stay in the same state. All right. There we go. We read a 1. Where do we go? Over to this state over here. We read a 0. So where do we go now? We go back to this state over here. Now we read a 1. And so we end up going, for the second time, back over to this state over here. And then finally a 0, going back to this state over here. Right? This one over here is an accept state. And by exclusion, this one and this one are reject states. So at the end, when we read throughout this entire input, what kind of a state did we end up with? Reject. So result is we reject. In other words, the interpretation here is 001010 is not in the language defined by this finite state automaton. Yeah, go ahead. The coloring here, right? This is a double. This is a double circle, and that's just the convention. Of course, with the actual definition, what you would do is you would designate a subset of states to be accepting states. Then the rest of them are rejecting states. So the model of computation is when you read bit by bit by bit, whatever state you end up in at the end of it, it's either a reject state or an accept state. If it's accept, then it's in the language. If it's a reject, like this was, then it's not in the language. Right? So let's go ahead and look at a couple more examples with this particular one. 0, 0, 0, 1. There we go. So where are we going to go end up here? We start here, 0, 0, 0, and then 1. So is that in the language or not? We accept. And it is in the language. This one was not in the language. Okay? Give me another string. 1, 0, 1, 0, 1. Okay. So 1, 0, 1, 0, and then finally 1. So do we accept it or not? Accept. And it is in L. So I'm starting to see a pattern here. Maybe it's that any string that ends with a 1, is that what this language is? Well, let's try one more. 1, 1, 1, 1. So come in here. 1, 1, 1, 1. Did we accept? Nope. Oh, okay, so my original hypothesis is wrong. If you look real hard at this, what do you have to do to get to this accepting state over here? You have to end with a 1. True enough. So, and then this is the end. But it can't have a 1 before it. Why? Because if you had 1, 1, then you jump all the way back at the beginning. Okay. So in order to get to this accepting state, this final accepting state over here, you would have had to get to this state. How do you get to that state? Either by seeing a 0 or by seeing a sequence of zeros. So it has to end with a 0, 1. Does it matter what comes before that? Nope. So sigma star is any other string formed by zeros and ones, including the empty string. This is a regular expression that is equivalent to this finite state automaton over here. So as long as it ends with a 0, 1, it's in the language. Let's try it out. 1, 1, 1, 1, 0, 1. Right? Again, you'd end up 1, 1, 1, 1, 0, 1, and you end up with an accept state. Try anything else that does not end with a 0, 1. In fact, what about 0, 1 itself? 0, 1, accept. What about 1 itself? There you stay in that initial state. What about the empty string? So the empty string, you don't read any inputs at all. That's why you need an initial state. The empty string always starts out in the initial state. Is that an accepting state? Nope. So we reject. We rejected this one, and these two we accepted. So what does it mean for a finite state automaton to solve a problem? It means that if you ran that finite state automaton on any input, for all inputs that are in the language, it would accept. For all inputs that are outside the language, and are not in the language, it would reject. So for this one particular example, we were able to create a finite state automaton for it. Let's look at one more example. In fact, oh wait, was this the same one? Yeah. Where's the other one? Okay, there we go. I wonder what that does. So give me some things that are in the language. In L, not in L. So give me some things that are in the language. 0, all right. 1, 1. I buy that. 0, 0. Okay. Give me something that's not in the language. All the empty string. Lambda. 1. 1. 1 goes from, you start in the state and then go to 1. Oh, you're right. Sorry. I was looking at that. So 1. 0, 1. What about 0, 0, 1? Okay, that looks good. Dot, 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 dot. All right. Let's design one. Instead of me starting out with a picture here, let me give you a language, and then let's come up with a finite state automaton for it. All right. So let L be the set of all strings x such that x contains an equal number of zeros and ones. All right. So for every 0 that you see, you need to make sure that you have a 1. All right. Let me start out with an initial state here, Q naught. Now the empty string. The empty string has no zeros and it has no ones. So should we accept that or not? Yeah, 0 is equal to 0, hopefully. In fact, you know what? Oh, so much better. You know. Oh yeah, there we go. All right, so if you see a 0 now, let's go to a new state. In fact, let's go ahead and make a new state. And let's go to that new state with a nice arc. I can't do an arrowhead. Maybe I could do an arrowhead, I don't know. Nope. I can't do a nice arrowhead. There we go. So suppose that you saw a 0. Right? Should you accept? Nope, because you've only seen one 0. So what if you see another 1 though? If you're in this state and you see another 1. I'll call this Q1. Where? Here? So if you see a 0, you haven't seen a corresponding 1. But if you see a corresponding 1, then go back and accept. I've seen a 0, I've seen a 1. Oh, okay. All right. What about the other, is this all the transitions there are? No, what other transitions do I need? What if I start in this state, I've seen a 0, I go over there. What if I see a 1 though? Okay, so which one? A third one? Okay. And what'll that be? Q2. All right, so, well, you know, what if I see a 1, I go over here. Yeah. But then if I see another 0, I could go back, okay. But that's just a superfluous representation of this over here. Right?
I think it's the opposite, isn't it? If we get a 0, we get a 1. If we get a 1, we get a 0.
Okay, sorry, yes. But do I have any memory here? Do I have any memory of how many 0s I've seen so far? I only have memory of the last one that I saw, right? Is there a way to count? I've seen 1, okay, 1, 2, 3 zeros. Now I need to make sure that I have 1, 2, 3 ones to correspond to those things. So is there a way to count with a finite state automaton here?
You wouldn't be able to count arbitrarily high.
You can't count arbitrarily high. You can count to a constant, but that still is not going to help you in general here. When we come back next time, I'll show you how to do this without counting, and then we'll roll the rest of that into, well, if you can't count, does that mean that there are things that you can't solve? And most definitely yes. All right, we'll continue on Wednesday then.
You could say you could count on it.